Introduction to Nuclear Technology. Chapter 5. Advanced Issues in the Fuel Cycle. Interactions between issues. This is a very personal presentation in that it concerns topics with which I was directly concerned from 1989 until 2001 when I retired, looking towards ways in which the nuclear energy industry might deviate from the path on which it is currently set. All are intimately related in that decisions made in any one area would have a substantial and usually direct influence on options available to the others, while themselves influenced or indeed constrained by decisions made there. None could therefore be considered in isolation. Basic issues. Two of these topics, separately or together, underlie all the others. Concerns about risks of weapon proliferation, specifically involving plutonium, and safety, largely in connection with long-lived radionuclides in wastes. Weapon proliferation. The correct operation of a plutonium bomb depends upon imploding a shell of the metal, initially subcritical, into a compact supercritical configuration at the same time as an artificially generated burst of neutrons initiates multiple simultaneous fission chains. It depends on the use of plutonium-239 with very little plutonium-240, more prone to spontaneous fission that would be likely to cause a low-yield premature explosion, dispersing the material before it had reached the required compactness. Civil plutonium, the product of a power reactor, has experienced prolonged neutron irradiation that generates substantial amounts of the higher isotopes. Whether it could serve effectively as a nuclear explosive is therefore disputed. Nevertheless, a device made from it could cause substantial damage and at the very least severe problems from the spread of contamination. Such an event could not be tolerated, and there is a consequent anxiety to prevent plutonium from falling into the hands of rogue states or terrorist groups. For that reason, from the start of the Carter presidency in 1977 until about the turn of the millennium, the USA not only ceased reprocessing civil fuel itself, but tried to persuade other nations to abandon the technology. In contrast, the UK, along with France, Russia and Japan, have, to varying degrees, always favoured recovering uranium and plutonium with a view to future use. They regard physical security and safeguards under the Non-Proliferation Treaty as adequate. In any case, there is an argument that the threat comes not from the large and increasing stocks of civil plutonium held under secure conditions in countries such as the UK, but from the possible theft of a small proportion of material held more vulnerably elsewhere, or from technologies unrelated to the nuclear industry. Plutonium security issues. On the other hand, there is still pressure for direct disposal of used fuel on the grounds that it puts the plutonium content immediately out of reach. However, the fission product content that provides some protection from theft decays with a half-life of about 30 years at this stage. There are fears that in the course of time a repository could become a plutonium mine. In contrast, plutonium in a thermal reactor would be definitely inaccessible, with quality degraded still further. Towards the end of the 20th century, the USA therefore started to consider separating plutonium as an aspect of waste management, emphatically not to be confused with recovery for utilization, and regarding uranium as a waste product, the principal distinction from conventional reprocessing practice. It has now moved further towards taking recycling more seriously for its own sake, and extending it to include special treatment for long-lived radionuclides. Long-lived radionuclides. There are two groups of such nuclides. Actinides, uranium, plutonium, with the very much less abundant neptunium, americium and curium, with the main emphasis on the minor actinides, which unlike uranium and plutonium are directed into waste streams in reprocessing plants. And then various fission products widely scattered in the periodic table. Being generally alpha emitters, the actinides have high radiotoxicity. How far that translates into real danger is debatable, but they move relatively slowly in the environment. The fission products, as beta-gamma emitters, are considered less radiotoxic, but are more mobile. Most attention has been given to the minor actinides. Minor actinides are generated by a chain of transmutation and decay reactions from plutonium. The anxiety over long-lived radionuclides rests on two possibilities. First, that by natural processes over thousands of years they might be leached from a waste repository and contaminate drinking water supplies, and second, that after the location and purpose of such a repository has been forgotten, it might be inadvertently penetrated by drilling operations, returning some of the content to the surface. The likelihood of accidental intrusion is completely unpredictable, though evidently low. Transport in the movement of groundwater can be modelled, but with many uncertainties, so very large safety factors are applied at each stage of the calculation. Significance of seepage. Even without the uncertainties in the calculation, the actual risk due to low-level radiation is almost impossible to estimate realistically. The best that can be attempted is to set an upper limit. As explained in Chapter 1, a linear relationship with dose is assumed in the absence of reliable evidence for any other, and without it, no estimate is possible at all, unless even more unreliable assumptions are made about the distribution of dose within the exposed population, whatever that may be supposed to be. Nevertheless, various casualty figures have been claimed with an appearance of confidence and look alarming. Much work has therefore been done on the idea of converting long-lived radionuclides to shorter-lived products. This would be done by partition and transmutation, otherwise P&T, separating the long-lived components from highly active nuclear waste and irradiating them in an intense neutron flux. The problems are that, first, americium and curium, among the prime candidates, are chemically very similar to the lanthanide elements that form a substantial proportion of the fission products and are themselves particularly strong neutron absorbers. Second, ways would have to be found to separate long-lived fission product elements from the general mass. And third, even if separated, most of them are for various reasons unsuited to transmutation. A P&T program is therefore unlikely to be completed without extreme difficulty. The claims for the benefits of what can reasonably be done are questionable, while it is seen by regulators as complicating an already difficult task of surveillance. Moreover, it might raise further issues of weapon proliferation, and in requiring additional processes on the most radioactive stream in a reprocessing plant, it would almost inevitably increase operational doses. However, research continues, although there are grounds for suspicion that the reasons may be essentially political. Most of the work has been done on the actinides neptunium, americium and curium, which might perhaps be separated from wastes by an extension of existing solvent extraction technology. First, separating them together with the lanthanides from the rest of the high-level waste, and then from the lanthanides. Some very impressive development work has been done, especially in France, which on the instructions of its parliament has devoted a substantial effort to producing selective reagents. Whether their use would be industrially viable may be another matter. One scheme that might be adopted without too much difficulty in a future reprocessing plant is to divert neptunium, less lanthanide-like in its chemistry than the higher actinides, into one of the main products, probably the plutonium stream. A very much more ambitious enterprise would involve further subdivision of the high-level waste, as in a Japanese proposal for a 4-group partition. The idea here is to separate bulk fission products into actinides to undergo fission either directly or after transmutation, technetium along with rare metals such as the platinum group that would substantially augment natural resources, heat-releasing elements cesium and strontium, which after a few centuries would have decayed enough to allow shallow disposal, and others that could be packaged into minimal volumes and disposed with no need to allow for dissipating decay heat. So far, the work on such schemes seems to have been at a more or less academic level. Whether any commercial reprocessing organisation would take it seriously remains to be seen. Consumption of plutonium and minor actinides. Any scheme involving transmutation requires an abundant source of neutrons, which in present reality means a fission reactor of some kind. The snag is that uranium-fueled reactors generate more of the transuranic elements that the purpose is to destroy. Fuels based entirely on the transuranics might be used, but with the drawbacks of instability, risk of runaway, and a rapid decline in reactivity that would require frequent refueling or an excessively wide control range. Consequently, there has been much interest in using accelerator-driven subcritical arrays of fissile and fertile materials that would virtually eliminate risk of runaway reaction and tolerate a wide range of reactivity. The principle of accelerator-driven systems is that a sufficiently energetic proton striking a heavy metal such as tungsten causes atomic fragmentation, releasing, say, 30 or 40 free neutrons. Current accelerator technology cannot achieve a beam of sufficient intensity at the right energy for a worthwhile rate of transmutation. But if the tungsten target were embedded in an array close enough to criticality to amplify the neutron flux by an order of magnitude, then the scheme might be viable, while the fission chains, although finite, would generate enough energy to drive the accelerator with a useful surplus. Accelerator-driven systems have been promoted for consuming fissionable materials with adverse reactivity coefficients or rapidly declining reactivity, and indeed as power generators in place of conventional reactors, with their alleged propensity for runaway reaction. Chernobyl is always cited, although the reactor there was of a uniquely unstable kind. A scheme for several accelerator-driven units was proposed for an area near Zaragoza in northern Spain, but apparently defeated by local opposition. Latterly there has been some revival of interest, although evidently with little understanding of the issues. For one, the risk of runaway is indeed avoided, but it is not significant in current power reactors, and the greater risk of meltdown due to decay heat after loss of cooling, as at Fukushima, still remains. Secondly, the system is expensive, not only requiring an almost complete conventional reactor, but a proton accelerator beyond current technology, and unlikely to be reliable enough for a supply to the electric distribution grid. Third, the development of adequate accelerators could create further opportunities for weapon proliferation. Another way advocated for dealing with the issue of transuranic elements, or rather of largely avoiding it, is to use thorium as fuel instead of uranium. Thorium in nature has only one isotope, thorium-232, that resembles uranium-238 in being fertile but not fissile, and indeed is still less fissionable. There is a close formal parallel between uranium breeding plutonium and thorium breeding fissile uranium-233, which is even better than U-235 as a fuel constituent, in that its higher neutron yield raises at least a hypothetical possibility of genuine breeding in a purely thermal regime. Certainly, prolonged residence appears possible, with little decline in reactivity after an initial dip due to the relatively long half-life of the intermediate thorium-233. This feature, however, has another disadvantage in forcing breeding to compete with further neutron absorption by the intermediate, withdrawing both a neutron and a nucleus from the breeding cycle, the more probably the higher the neutron flux. Thorium could, in principle, be used in any kind of reactor: thermal, fast, solid or molten salt, free-running or accelerator-driven, but is particularly associated historically with high-temperature reactors, in which an ability to tolerate a smaller proportion of fissile material gave it an edge over uranium. The present abundance of plutonium nullifies that advantage. Nuclear side reactions generate small amounts of the relatively short-lived, 70-year half-life, uranium-232, with a decay product, thallium-208, that has exceptionally energetic and penetrating beta-gamma radiation. Even after separation from fission products, uranium-233 generated in a reactor would therefore need remote handling unless further operations were completed almost immediately. Within a week is suggested. This is claimed to render it resistant to weapon proliferation, although it seems unlikely to deter proliferators unconcerned with danger even to themselves, except insofar as it would render a device hard to conceal from radiation detectors. Two undoubted advantages of thorium over uranium are: first, it minimizes production of transuranic elements, although in protoactinium-231 it generates a long-lived actinide of its own, while the range of fission products from U-233 is much the same as from other fissile nuclides. Second, its near breeding capacity favours high burn-up. There have been suggestions for small, self-regulating reactors, fueled for life, to be supplied to technologically backward states and eventually returned intact to vendor. Thorium is more difficult to reprocess than uranium. Both metal and oxide are resistant to nitric acid without a catalyst that would add to eventual waste, while the nitrate is less extractable into the usual solvent compared with uranium or plutonium. Spent thorium fuels would therefore probably be disposed directly. In the 1990s, the IAEA was urged to recommend a fuel designed by Alvin Radkowski with a highly reactive seed surrounded by a blanket largely of thorium that would stay in a conventional PWR for perhaps 9 years with 2 replacements of the seed. Despite doubts about its practicability, a test irradiation was set up at the Kurchatov Institute in Moscow. It should have been completed years ago, but results do not appear to have been published, and material about it has vanished from the internet. Thorium has long been used in India, which has extensive deposits of the ore and relatively little uranium, and the technology there is highly developed. Elsewhere there is little industrial interest, as a complete new infrastructure would be needed in order to adopt it, especially in view of the high radiotoxicity, about 10 times that of uranium. Open versus closed cycle operation. A closed cycle with thorium will be difficult because of the reprocessing problems, but uranium fuels have been reprocessed ever since the start of the nuclear age, with a view in the civil sector to recycling. Nevertheless, the merits of such closed fuel cycles as against direct disposal are still being discussed. For the open cycle, it avoids reprocessing and the sequence of complex and expensive industrial operations, while direct disposal is relatively straightforward. There are fewer public objections to an open cycle. With HTR-type fuels, reprocessing is scarcely practicable. Since remaining fissile content is protected against theft by intimate association with intensely radioactive fission products, proliferation is much less easy than after separation. However, this protection slowly fades. Direct disposal wastes potentially valuable resources, though probably less with thorium than uranium. On the other hand, a closed cycle is essential in a regime including fast reactors. It therefore allows maximum utilization of a finite resource, and in principle allows destruction of long-lived waste radionuclides. It generates a great deal of secondary waste in materials and equipment. It disperses mobile nuclides such as iodine-129 and krypton-85, and it is substantially more difficult with thorium than uranium. If we're thinking of new types of reactor, whatever we choose must at least have a minimal risk of runaway reaction or losing coolant, be much less expensive in real terms than current equivalent types, defend the fuel content against possible diversion, be as far as possible impervious to operator errors or malpractice, and finally, be as simple as possible to decommission at the end of its useful life. Of reactors that might be used in the coming years, light water types, whether boiling or pressurized, are currently dominant and likely to remain so for the foreseeable future. However, they generate plutonium and minor actinides and are inefficient in consuming them. If this becomes a more serious issue, fast reactors or an equivalent would be needed. Interesting can-do type reactors may increase on account of their outstanding neutron economy that could permit their use of spent light water reactor fuel with minimal preparation, or very long residence of near-breeding thorium fuel. HTRs could also become important because of their greater thermodynamic efficiency in electricity generation, or possible direct supply of industrial process heat. The resistance of the fuel to mechanical or chemical degradation would be a great advantage in direct disposal. Special types might be designed for developing countries, for instance, fueled for life, capable of automatic load following without operator intervention, achieving high burn-up in once through mode. And perhaps in the more distant future, molten-salt types could be developed for use in either fast or thermal neutron mode. Fast reactors are likely to be essential sooner or later, unless some viable alternative to fission energy emerges. But there are various issues specific to them. A meltdown of the fuel could possibly lead to a more reactive configuration than in the intact state, with no possibility of control. Current fast reactors are cooled by sodium, which is itself chemically reactive and highly flammable, therefore requires discharged fuel to be scrupulously cleaned before anything else is done with it, has a relatively low mass number and so softens the neutron spectrum, is somewhat neutron absorbing, so that its loss would increase reactivity. Some of these difficulties might possibly be overcome by replacing it with lead or helium. A molten-salt system might avoid all these problems, with the fuel continuously circulated between reactor, steam generator and cleanup. A great deal of valuable, or at least highly interesting, work has been done on these various issues. Much of it, however, has been done under political pressure, or with exaggerated claims of benefits to be expected, such as preventing nuclear terrorism, when the main risks of it are elsewhere. The known existence of funding has attracted much attention from laboratories suffering after the curtailment of military research. Indeed, some of the funds were provided expressly to counter any temptation on individuals to work for rogue states or terrorists. There has been a tendency for specialists in particular areas to make false assumptions about relevant issues in others, sometimes with absurd results. Much of my own work was simply to apply some logic and factual information to the discussions.